Okay, so I think we are ready to start. It's now 5 past. So as usual, we'll start with a brief overview of what this event is going to cover. First, I'm going to be presenting in just 10 minutes some of the recent updates about Flower. Especially today, we're going to be talking about the Flower AI Summit that took place just 2 weeks ago in London. I'm going to summarize all the announcements, and also I'm going to briefly go through the Flower 1.8 release that was just released early this morning. Then after that update, we are super lucky to have 2 great speakers that are going to tell us everything about their latest research. We're going to hear from Philipp, how he's making federated learning more carbon efficient. And we are going to hear later about adaptive compression, the newest methodology for adaptive compression in FL from Francesco. So without further ado, let's start with what happened in the second week of March. So we ran the Flower AI Summit 2024. It took place in London. It was a 2-day event, 1 day for research and another more focused on industry. And I think this was the most successful Flower AI Summit ever, with over 1,000 registrations, and many of you were there in person. For example, this photo you see here is the venue fully packed when Daniel started the Flower Summit in March the 14th, I think it was. So the first day, as I said, it presented the latest research in federated learning. Some of you might recognize some of the speakers: Judith, Virginia, Andrew Sultan, who is in fact the one on the picture on the right. Also, we heard from Hui and from Borja. We had also a poster session, which I believe it was more than 20 posters. And we have our speakers today are in fact 2 researchers that presented their own posters. We also had on the second day an event, a day focused more on industry and how federated learning is changing how industry applies AI to products and services. We heard from Tim from Samsung, Nathan from the US Air Force, from Sari from AWS, and Mina from Volvo, as well as from Roman, who showed us how to integrate homomorphic encryption into Flower. I think that was a super interesting event because, at least from my side, we mostly focus on the federated learning research. But when you see how all these amazing tools are used in industry to create real products for people to use, I think is so much more inspiring in most cases. And then throughout these 2 days, we were also presenting and providing an overview of what Flower Next is, which is what I'm going to be talking in the next slide. But I want to highlight a few other components that are also part of Flower Next, and some are complementary to Flower Next, which are the support for LLM fine-tuning in Flower. This is something we call LLM Flower Tune, which makes it super easy, almost trivial to federate the fine-tuning of a large language model to your own data that, for example, you want to keep it private. There is an example that you can run today, even if you only have 1 GPU. And it doesn't have to be a super powerful GPU. You can run it with almost any standard gaming-grade GPU. We also announced the Flower Discuss, which is a new platform we are starting in the Flower community to help to have more engaging discussions, especially when you have some questions, for example, on how to build something with Flower. We have seen this works super great in Slack, but we're giving it a try also to discuss, to see how these discussions can evolve, maybe potentially in a different way, involving more of you. And then finally, we got a big preview of the now released update to Flower datasets, which makes it easy to download and partition and preprocess datasets. So all the work you put in your federated learning projects, you can focus on the algorithm and the different setups of your particular federated learning application, and you don't have to worry so much about am I doing the right partitioning or not, which is a bit of a complex task. And then finally, we also launched an update, like the second iteration of the Flower pilot program, for which we got a lot of interest from folks in industry and academia. And if you haven't yet heard about it, please go to our website and you can read everything about it and consider applying. And also, if you were not able to attend the Flower AI Summit or you missed part of it, all the recordings of all the keynotes and other talks are available in our YouTube channel. I believe there is also the stream of the whole session is still online, so you can watch it non-stop if you prefer to do so. But if you go to our channel, you will find a playlist which has, I believe, almost 30 different videos for all the content that was created for the Flower AI Summit. So this was a summary of the Flower AI Summit that took place in March. And what I want to do now is to very briefly, but go through what are the bigger updates in Flower 1.8 that is already available. So for example, you will see, if you take a brief look at this slide, you will see that almost everything is about Flower Next. We have been making huge progress towards this goal of making Flower much more versatile to run more complex workloads and adapt to more sophisticated setups in simulation and also in real-world deployments. And we're happy to announce that Flower Next, the high-level API, the one that probably you are already familiar with, like using strategies and so on, is stable. The low-level API is in preview mode. There are some examples in our repo that allows you to get a glimpse of how it looks like. And if you are keen on seeing what's the latest thing in Flower, I really invite you to take a look. We announced Flower mods, which are mods stands for modifier. These are like plugins that you can embed into your Flower applications so they gain some particular functionality. For example, let's say you want to log all the communication that happens between your clients and the server. You want to add some custom logging, or you want to compress those updates that the server sends to the clients, or vice versa. You can do that with mods without having to change the client code or the server code directly. Those are some examples. There are some examples about mods that enable you to plug, for example, differentiable privacy or secure aggregation. Those are mods that are already available in Flower, and there are examples showing you how to do that. Of course, we have also the LLM Flower Tune, which was built around some of the latest functionality in Flower Next. Flower Next also will be able to run, you will be able to create a completely full projects in Flower with something we call the Flower CLI tool. For example, if you do Flower New or Flower Run, you will be able to create currently a basic Flower project, but over time we are going to evolve it to make it much more versatile. So creating a starting project will be as easy as typing a couple of commands in your terminal. We have introduced also the new Flower simulation engine, which has been rewritten completely and is fully compatible with Flower Next. And also in this release, we also invite you to take a look at all the new examples that have been introduced, like federated fine-tuning of RDIT, for example, and many more examples that have been updated to Flower Next or will be updated to Flower Next in the coming weeks and months. And if you are very keen on contributing to Flower, feel free to take a look at examples. And if you want to update it to Flower Next, let us know and we'll help you with a pull request. So this is a summary of Flower 1.8. There is, as usual, a blog post that details everything that is in Flower 1.8 and much more than what I'm presenting here in the slide. So please go check our website if you want to see absolutely everything that is new in Flower. Okay, so that was an overview of what Flower AI Summit looked like and what the Flower 1.8 release contains. And now, without further ado, I'm happy to announce the first of our guest talks. This talk is titled Towards More Carbon Efficient Federated Learning, and it's going to be given by Philipp Wiesner. I hope I pronounced that properly, who is a research associate at EU Berlin. So Philipp, the floor is yours. Please go ahead. I'll stop sharing my screen.
Cool, great. Yeah, thanks for the introduction. So I'm Philipp, and I'm doing research on carbon-efficient computing systems, and since about 2 years with a focus on federated learning. And let me maybe kick off this talk by explaining what carbon efficiency means in the sense of computing. So in carbon-efficient computing, or carbon-aware computing, it's also called, we're trying to align the power consumption of a computing system, in this case now a federated learning system, with the availability of clean energy. And as you know, like the biggest sources of renewable energy that we currently deploy are solar and wind, and they are highly variable. So we basically try to consume energy where and when the sun is shining, for example. So we're trying to exploit these spatio-temporal patterns that arise from these energy sources. And in this work particularly, we're focusing on something that is called renewable excess energy, also called curtailed energy or stranded energy. And this always occurs if in a certain area of the grid, we have more supply than demand at a certain time. And this is actually occurring more and more often as we're deploying more and more renewables, because in the past, we only had variability on the consumption side, but we were able to fully control our power production. And now, additionally, we have uncertainty and variability in the production side. So we're a bit losing control. And these areas, these periods of times are becoming more and more frequent. And actually, they're highly problematic, because what are we doing with this excess energy? The most straightforward idea, of course, would be to store it. So we basically transfer it through time to use it at a later point in time. Now, the problem with energy storage is that it's really expensive, and it's always only available in limited capacity. So it doesn't really make sense to buy 100 or 1,000 of batteries if they're just idle 90% of the year, just to accommodate some peak loads. Additionally, we have conversion losses, we have increased battery aging with frequent charge cycles, and so on and so forth. So energy storage, it makes sense, and it's important, and it's able to mitigate the problem to a certain degree, but it's not really solving the problem. The second option that we have is transferring excess energy to neighboring regions. So we're basically transferring it through space. And here we have similar constraints. Also, grid capacity is limited. We're seeing this frequently in Germany, where we have a lot of very big offshore wind parks in the north of the country, but all the consumers, all the big industry is in the south or the west. And the grid in Germany is currently not strong enough to transfer all this energy to these regions. And additionally, excess energy patterns often correlate in neighboring regions because they have similar weather, for example. Now, if none of these two options is available, then the only thing we can do is curtail the energy. That means we waste the energy. We don't even produce it, or we transfer it into heat or something like this. Sounds stupid, but it's actually a common practice. So in 2022, the California system operator had to curtail around 7% of their entire solar power production. And Germany, as I said, curtails a lot of its offshore wind energy, and China had to curtail 15% of their entire renewable energy production that year. And here on the right, you can see that this problem is getting worse and worse as we are deploying more and more renewables. So one of the most important solutions is that also the energy consumers need to become more flexible. They need to consume less when no energy is available, and they need to consume more once the energy is available. And we're now applying this basically to data centers, and particularly to federated learning. Because it turns out that federated learning is a really good use case and a very interesting use case for this. Because not only we have a very energy intensive task, it's also spanning over time. So we have like this time axis to schedule on, and also it's geographically distributed, often even globally distributed. So we also have this axis. And today I'm presenting at Zero, which we will present at ACME Energy later this year, which is a federated learning system that tries to leverage this energy. So it's a FL system that operates exclusively on renewable excess energy, as well as spare computing capacity at clients. And this is also a very important requirement, because if you would need to buy new hardware to make this work, that would also not be very carbon efficient. And what we're basically doing is client selection. So we're trying to compute, again, when and where energy is clean. But of course, it's not that simple to just always select the cleanest clients. We have several challenges here. The first and most obvious challenge is, of course, we have a very volatile and a highly variable environment. So clients can appear and disappear at any time. They might not be available for longer periods of times if there's no excess energy. So how can we guarantee a fast and efficient training in these environments? The second problem is that we might have common power budgets between clients. So in FedZero, we are mostly considering cross-silo federated learning for the reason that in cross-silo FL, we have usually quite big, powerful, and also power-hungry clients. So a single client can be an entire GPU cluster that consumes hundreds or thousands of watts. And here it really makes sense to address the scheduling problem, because in cross-device federated learning, clients, like individual clients, don't consume a lot. And if we now assume that, for example, we have some excess energy in the UK, it's maybe not the most relevant mitigation strategy to turn on 50 iPhones in that region. So this is why we're focusing on cross-silo FL. But here in cross-silo FL, clients are often co-located. They can be co-located in the same data center, in the same region, and then they often share the same power source or same power purchase agreement. I will talk about that later in a second. The third problem, and that's the most challenging one, is fairness. It's, of course, a big topic in general in machine learning and in federated learning as well. But here it's even worse, because we introduce a lot of unfairness if we bias our client selection strategies to select green clients. And some clients might have a lot more energy available than others. So we really need to take care that we are not introducing biases towards these clients. And lastly, of course, we want a system that is not only scalable, but also robust to forecasting errors, because we're doing our entire client selection strategy based on forecasts of free capacity at clients, as well as renewable excess energy. So we need to handle the problem that maybe at runtime we have vastly different conditions than we expected. And turns out that this all boils down to a big trade-off between final model performance, the convergence speed, and carbon efficiency. So usually we're optimizing for the upper two. We want, of course, well-performing models. And during training, we want fast convergence. And now if we also introduce this carbon efficiency point, we need to sacrifice on at least one of the two. And FedZero does not sacrifice on the model performance, but we sacrifice on convergence speed. So under certain conditions, maybe we need to slow down the training, or maybe even pause the training for some hours to wait until some clients that we consider valuable become available again. I'll now give you a quick overview. I don't want to dive too deep into the approach, but I give you a quick overview about the protocol and the system architecture of FedZero. So in FedZero, as I quickly mentioned before, clients can be co-located under the same power domain. A power domain can actually be a power source. Could be that your data center has some solar panel on its roof, for example, and multiple clients feast from this common energy source. But could also be that this is maybe a power purchase agreement. So you're basically promising some big wind park that you're like buying a certain amount of energy at a certain time and a certain location, and you're powering multiple data centers with this energy. So still multiple clients fight for the same energy source. Now, at the beginning of each training, clients need to provide certain information to the server, which is their computing power, their energy efficiency, and also which power domain they belong to. And after the server gathered all this information, the first round can start, and the server queries forecasts. It queries forecasts for spare capacity at clients. So we do load forecasting at clients to identify when in the future we might have underutilized hardware. And as well, we're querying forecasts for renewable excess energy. So this is mostly based on weather forecasts then in most cases. And after all these forecasts are collected, we can run our optimization problem. which I'm not going to explain in detail. But what we're doing is we're cherry picking clients that have a high system and statistical utility. These two metrics are very, very common in client selection approaches. So we want fast training rounds and we want valuable training rounds. And also, as I said before, we want to take care of fairness. This is also commonly done in client selection. And now here, additionally, we also need to take care of this co-location problem. So since excess energy is a limited resource, we generally want to spread our client selection across many power domains, because if you would select all of these 3 clients, they all have to run on the same limited resource, they might slow down the training and we have slower rounds. So this is our client selection. So now we select a certain subset of participants and tell them to start training. And this is where it gets really interesting. This is a topic that we also continue researching on. At runtime, of course, we might have very different conditions than when we forecasted. There might be more energy, less energy, more capacity, less capacity at clients. So they continuously need to communicate with some controller that then adjusts the pace and maybe tells a client to slow down a bit, consume a bit less energy, or tells it to speed up. Because in the end, we have the overall goal that all clients finish roughly at the same time. So we avoid stragglers and have fast and efficient rounds and really utilize the infrastructure and the energy that we have available. And the rest is common procedure. We aggregate all the results. The aggregation strategy is none of Fedzero's business. You can use whatever you like. And we start the next round with very new set of forecasts. Now, as I said, I do not want to go into detail about the client selection or the fairness mitigation or something. But since this is a Flower monthly, I would rather want to talk about how we implemented this in Flower, because this was actually quite challenging. So our evaluation is based on real solar data and real solar forecasts that were provided by Solcast. That's a big solar data provider, as well as load traces based on the Alibaba GPU cluster data set. It's also a very commonly used data set for systems evaluations. And for Fedzero to show effect, we need long trainings. We need really to train over the course of many days. So we execute our trainings over 2 weeks. And now you can maybe already see the problem, because for our final experiments, just for the final table in our paper, basically, we had 2 energy scenarios. One where all the power domains are co-located. It's 10 cities in Germany. So also all the excess energy patterns are very correlated. And the second scenario, we have a globally distributed setting. Now we have 2 scenarios. We evaluated 8 approaches or different parameterizations of approaches on 4 different model dataset combinations. And for each experiment, we are doing 5 runs. So this, just for the final table, results in 320 runs. And at least in my lab, we don't have 320 GPUs available, nor do I have years of time. So we needed to come up with a solution to evaluate this a bit more efficiently, because this does not only even cover like the entire experimentation phase, ablation studies, other experiments we did. So what we did in the end, we do perform actual federated learning trainings, but we're simulating the environment and we're simulating time. And we did this by implementing a custom server in Flower that allows discrete event simulation over time series datasets, about time series traces, like, for example, these load traces. And this enables us to do experiments faster than in real time. And also very important, it enables us to skip over periods where no training is performed. So here on the right, you can see in this co-located scenario between 8 in the evening and 4 in the morning, there's no energy available ever because it's night. So we can just skip over those 8 hours. We don't really need to wait. And we implemented the server in a way that at the beginning, it performs, at the beginning of each round, it performs the client selection. So we have a 1-minute step size in our discrete event simulation. And for every 5th minute, we have an entirely new set of forecasts that we previously crawled from Solcast for the next couple of hours. So it performs the selection. It then simulates the real-time behavior of our training rounds. So now we're using like the real traces and not the forecasted ones. And what comes out of this is basically the amount of mini batches that each client would have computed during the next training round. And then we communicate this number to the clients and use the normal Flower simulation utility to execute the training. So this works well. And I would say the first part and the third part are also sound. But to be honest, I think the second part is a bit of the weak spot of our evaluation in this paper. Because it's really hard to simulate real-time behavior unless you execute the real-time system. It's really hard to say what happens when a client has to communicate to the controller has to take a decision, there's communication delays, maybe not everything works out as we planned. So this is only an approximation, of course, how the system would behave in reality. So this entire part here is only simulated so far. Of course, I wouldn't put that big of a focus on it if we weren't working on a solution, because now since about a year, we're working on a co-simulation framework, and now I'm moving on basically to ongoing and future work. It's called WESM. It's a big testbed for carbon-aware applications and systems, so it's for computing systems that have to interact with the energy system. And what WESM is we basically took a bunch of already existing domain-specific simulators, so that's simulators for power production, so solar power production, wind power production, as well as battery simulators, grid simulators, and we plugged them all together in a big co-simulation framework called Mosaic. And what Mosaic does is it takes care that the simulators run in the same pace and that they're also able to exchange messages during runtime. And we basically plugged all of these simulators together and built a nice interface around it. And then now what you can do in this example now for federated learning, your federated learning clients, no matter if they are real clients like real devices or simulated devices, they would periodically communicate their power usage to a microgrid simulation, and you can have multiple of those in parallel. And then WESM takes care of simulating basically what the energy system would do by also in parallel running power production simulators and so on. And then you as a user are able to implement controllers. And a simple controller, for example, could be a monitor, which just periodically writes down the state of the energy system to your disk or shows it in a graphical user interface or something. But you're also able to implement an API server, like some REST server, that gives visibility and control to your computing system at real time. So this is called software-in-the-loop simulation. So while your training is running, your federated learning client can actually query this API and ask, okay, how much energy do we have available? What are forecasts? What is the state of my simulated battery? And so on. And from the point of view of the federated learning client, this is supposed to behave like a real energy system. And it's, of course, highly scalable because it's all simulated. I think this will open up a lot of very interesting new research directions if you really go into a bit more depth of how federated learning systems can interact with their energy system. And we currently have a lot of ongoing research projects that try to make this a bit more usable in Flower and maybe come up with some nice interfaces between FL systems and energy systems. We're also trying to make some evaluations how well these simulations perform compared to real hardware test beds, and so on and so forth. And with this, I'm already coming to an end. So I presented FedZero, which is a federated learning system that exclusively runs on renewable excess energy and spare computing capacity. And what we're currently working, and FedZero here, it's the code is open source. You can look at it on GitHub. It's all implemented based on Flower. And WESM is this co-simulator that I just talked about. You can also try it out already. We have some documentation, and the API is pretty stable by now. As I said, we're working on it since a year or more. But of course, a lot of stuff will improve. WESM also comes with all the data sets that we used in the evaluation for FedZero. It comes also with some more data sets on carbon intensity that were provided by Wartime. And give it a try and feel free to reach out to us. And thanks for your attention.
Okay, well, I think this was an amazing talk. I have from Slack a couple of questions.
Mm-hmm.
And if the rest of the audience in the meantime can think about some questions if you feel like asking something. So the first question I have is related to when you were talking about FedZero, you were describing 3 steps you follow to run the huge experiment. And you were saying that the second one was the most complex one. So the question is the output of part 2 like a series of configurations that your strategy would send to its client, like, configure fit in Flower in the strategies? Is this the output of part of the step 2 here? For the client to receive it and know, I need to, because I'm in a peak of a lot of excess, I can train for 1,000 batches instead of 10 batches.
Exactly. Yeah, it's like that. So the simulation is also an optimization problem. It gets as an input basically the expected amount of work that the first step comes up with. So the first step says, okay, I'm expecting this and that client to compute 60 mini batches during the next round. But it's doing that based on forecasts. And now in the second step, we're like approximating how the system would behave now if we have the real traces. And with the real traces now, we of course know maybe there was less capacity available than we thought. So now out of this comes, no, it's not 60 batches that we managed, it's only 40. And then those 40 would be exactly communicated using configure fit to the clients, who's then executing the training.
Okay. So then this means that when there was no excess, like those, like for example, from 20 hours to 24 hours, clients will get like basically train for 0 batches, so you will exit immediately, speed up. So the round
we wouldn't even notify, we wouldn't even start the simulation engine.
Okay, yeah.
It would just loop over it until there's actually training to be performed. And then, but we do need the training to be performed because we need the output of the training for the next client selection round. So in our case, we need the local losses because we use them to approximate the statistical utility of clients.
The second question I have here is about testing. So the question is, does it make sense to connect so you were talking about this monitor controller.
Mm-hmm.
Would it make more sense to connect it to the strategy so it can then build the configure fit accordingly, or does it make sense to connect it instead to the clients?
Yeah, it's a very good question, and one that I do not yet have an answer to. That's exactly what we're currently also trying to investigate. I think there's probably different settings. Might also be a privacy issue. Maybe the server does not have access to all the energy system information. So the clients have to communicate with their own energy system and only give some more high-level infos like I'm available, I'm not available. I guess it depends on the setting, and this is what I mean. I think there's a lot of interesting research questions that pop out of this. But yeah, I don't know yet.
Okay, cool. Well, cool. Okay, I think those are the questions I see. I have one question on my own, which is, of course, has to be related to baselines. Do you think that Fed0 could be a Flower baseline?
Could be, but
or do you think, is it right? Oh, well, you have already open sourced it, I believe.
The code is open source. Yeah, you can look at it. DOS/group/Fed0. Mm-hmm. The thing is that we have this custom server that makes it maybe quite hard to implement it. So it really relies on this custom server that does the discrete event simulation. And the server basically keeps track internally of the time, but it's not easily integrated as a baseline, I guess.
Maybe I can take a look, and if we think there is an opportunity, we can discuss.
Yeah, absolutely.
Okay, great. I think these are all the questions. I don't see questions here on Zoom, so I think this is everything. I think this was super interesting talk, and also quite interesting to see how, depending on like the fairness issue related to the energy source you get. So that was something I was not expecting to see, but it's real. So super cool.
Thanks a lot.
Okay, thank you. Okay, so I'll share my screen. Okay, so our next speaker is Francesco Pase. He's a lead AI research engineer at NEWTWEN. And he's going to tell us about his latest work, which is titled Adaptive Compression in Federated Learning via Site Information. So Francesco, the floor is yours. Looking forward to hear everything about this work.
Thank you for having me. Let me share the screen. So thanks for having me. Today I'm going to present one of my last paper out of my PhD. And it's called Adaptive Compression in Federated Learning via Site Information. And this is actually, we present this paper at ISTAT 24 in 1 month. And this is a joint effort with Philipp and Isaac and Professor Stanley Koyeko and Wiesner from Stanford University. Professor Dennis Gould from Imperial College London, and Michele Zorzi from University of Padua. So in this talk, I will rather focus on the details of the basically the algorithm rather than on implementation. That is more standard flower implementation of that. So we start with just this slide that probably all of you are familiar with, and all of you know. This is like usual federated learning kind of pipeline. I just use this slide to point to you where I focus with this research. So again, the idea is basically to have their clients to train local models by using their local data without sharing their raw data to the server, but just rather to send and to share the model updates or gradient information to the server. And then the server can aggregate this information and produce a new global model to be broadcast back to the client. Now, this work will focus on the communication efficiency of federated learning, especially if you think about wirelessly connected devices, for example. We may have some problems due to network resource constraint, or we may also have some battery constraints on the edge device. And we know that the communication part is also can heavily impact on the battery lifetime of our edge device. So the idea is, how can we reduce the communication burden from the client to the server while performing federated learning in this kind of communication constrained environment or devices? So, of course, federated learning is becoming very popular, but the models are becoming huge. So this motivates somehow this research direction. You can think of, like, for example, also the flower efforts in implementing federated learning strategies for LLMs. These LLMs contains billions, if not hundreds of billions of parameters. And, these model updates and gradient updates, they have the same size as the model ones. So, of course, the communication bar is becoming quite a bottleneck. And the second observation is that the research literature is showing that models contain redundant information that usually it's not always so helpful in training such huge models. For example, you can see here just a few plots from this seminal paper on the battery ticket hypothesis, where basically the idea is we can remove a lot of connections, so a lot of information from the model, but still having very good accuracy performance. Of course, now there are a lot of new works popping up nowadays on LLMs and other huge models, where basically the idea is to prove, for example, to apply quantization, knowledge distillation to reduce the size of those models, and still preserving the accuracy. But third, a very important kind of observation is that many distributed learning strategies, for example, here there is a QHGD that is one of the kind of baseline for federated learning. That is a quantization version of stochastic gradient descent. The idea of many quantization or in general compression methods is to communicate stochastic samples rather than deterministic value. So what I mean by this is that you can see here on this very simple example, imagine we want to convey the value of just one coefficient of the network, and without all of the generality, let's keep in the 0-1 range. And let's say that the real value of the new update is 0.6. Now the idea is to quantize basically the range of possible values into a fixed and finite number of quantization levels. In this case, we have 5, we have 0, 0.25, 0.5, and so on. And if we have the new value as 0.6, the idea is not to send just the closest kind of quantization level, but rather to compute a probability distribution over possible quantization level, depending on the proximity of that point to those quantization levels, and then to draw a sample from these quantization levels and send that sample. Why we are doing this is basically because somehow in this way we can preserve the unbiasedness of the graded estimation then at the server side. So this is an important concept, and this is basically the idea behind our work. But before diving into that, I will just give a very brief detour of somehow information theory for communicating data. So usually what people in communication theory community use to model and to formulate the problem of communicating data, for example, like sending the updates from the client to the server, is we can think of the client as observing a sequence of random variables x1 up to xn, all distributed according to p of x. And the idea is that the client has to send this sequence of samples, for example, the sequence of new model updates to the server, by spending the minimum number of bits per symbol, that is the rate, So basically, we want to quantify the number of bits we have to spend per symbol, for example, per model update. We need to send a message to the server, and the server then has to decode this message in order to recover the exact same sequence X, for example, the model updates, the full model updates. Now, the question is, what is the minimum rate that we need in such a way that the server is able to decode exactly the same sequence of X1 up to Xn? And could Shannon provide, of course, the answer to this question in the seminar paper, and where basically he showed that as n goes to infinity, so as the sequence becomes longer and longer, we can basically code a message such that h of x bits per symbol, we can send reliably this information to the server. What is h of x? Is the entropy of the distribution P of x, actually, that has this shape that you can see here. This is not important, but the idea is that this is a very fundamental quantity information theory. So the entropy of the distribution coming from these samples. But now the point is, as I said before, usually all these compression quantization methods, they're not sending deterministic values, but rather samples coming from some distribution. So maybe the right mathematical formulation, and we were inspired by Polka's paper on coordination capacity. Here, the idea is maybe we don't want the server to exactly recover the exact sequence of sample that can be observed by the client. But imagine that this X1 up to Xn are the new deterministic updates of your model. Then what the client can do is apply some sort of quantization scheme like QHD that we briefly explained before. And by that, basically, the client can compute a probability distribution over candidate possible values for the new updates. And these are the Y1 up to Yn. That those basically new updates depend on the realization of the X1 up to Xn that have the real value of your model. But now the point is that the task for the server is not to recover the exact same sequence of Ys, but just to be able to sample according to a probability distribution that is similar to the one obtained by the client. So the goal for the server is to be able to sample those Ys, so the new candidate values for the model updates, according to the same distribution the client can observe. Now, this problem has, again, if you want to convey such information to a server, the minimum is the mutual information between the two random variables X and Y. That is basically the divergence between the joint and the marginal distribution. Now, what is the divergence is basically a measure that basically is a quantity that measures the discrepancy between two distributions. So the closer they are, the smaller the divergence, and vice versa if they are far apart from each other. And this is important because this will lead to some key observation for our work, where basically the first important observation is that this mutual information somehow measures the dependency between X and Y. So what I mean by this is if the new candidate values, for example, those Ys, does not depend so much from the new updated values locally, the real values X1 to Xn, then there is no need to send information to the server. The server can just sample according to distribution P of Y without knowing the realization of the X that is basically observed only by the client. So the rate is zero. It will be kind of clearer later why this is important. The second observation is that this quantity, so this mutual information, is always less than or equal to the minimum of the entropy of X, entropy of Y. Why I'm telling this because it's important, because if we want to use the standard way of communicating updates or data, that is the one that I showed in the beginning, we know that the minimum rate that we need to reliably send this information over some communication channel is the minimum of these two entropies. So it means that we can send basically the right task and the right goal for us is to send so those updates in such a way that the server is able to sample according to the new quantized level. And if we do this, then we can see that we can save a lot of network resources because, of course, the mutual information is always less than or equal to this lower bound for communicating data. And third, the mutual information can be written also as the average over P of X of the K divergence, again, between the probability distribution over the Ys, which is the marginal over the quantized model updates, and basically this conditional Y given X. So what this means basically is that if we have a global distribution at this phi of y, that we basically we interpret this as the global model that the server distributed at the beginning of each round. And we interpret the kind of conditional distribution P of y given x as the distribution over the new update condition on the training iterations performed by the client locally. For example, condition on the data set acquired by the client. Then we can see that this mutual information measure indeed the average basically gap between the optimized local distribution and the global distribution. So you can think of it as the information acquired by the clients locally during the local training stage, so the new knowledge acquired by the client. And this makes sense because we want to send no more, no less than this quantity. So basically, we just want to send the information that the new client is acquiring through via basically the local training stages. So given this, basically, we propose and design minimization of site information at this KLMS. And you can think of this as a new and independent block that can be applied on top of already existing strategies. So let's think, for example, of any kind of local training strategy. The idea is, as long as we can interpret or we can basically represent this new model updates by some distribution Q of K is the client kind of index, we can apply KLMS on top of this and sample a new message that can be sent to the server by spending at most K divergence between Q and P, kind of peak curve new model update. And of course, there are some algorithms that are more fit for this kind of strategy, but all kind of quantization method can use this. All Bayesian method are can naturally use this, and other algorithms that I will brief with us later. So the key point is that we can represent the local knowledge acquired by the client via distribution P of K, and the global knowledge via distribution P that is known both by the server and also by the client. And then we implement some sort of important sampling style algorithm to create the messages. So basically to compress and to represent the local updates and send them to the server in a very communication efficient way. So let's assume that we want to send, for example, one layer of a neural network. This is just for brevity. It is just 8 kind of coefficients. So we have 8 coefficients we want to send to the server. What KLMS can do is basically to group these coefficients into also non-uniform kind of groups. As you can see here, we may be able to group the first 5 and then the last 3 of them. And by each group, basically KLMS will compute a message and send this message to the server. So why this is important? Because previous work only considered kind of uniform pairing of those coefficients in the network, but also in centralized setting with these kind of slightly different approaches. But what we observed by performing some simulations, some experiments, is that the information, usually federated learning, is not uniformly distributed over the network and over the route. So what I mean by this, basically, you can see here that in this 3D plot, we measure this K divergence, so this discrepancy in the local and global knowledge. So basically, this is the information gain acquired by the client while training the local model. And we can see that this new information is not equally distributed over the layer of the network and also over the route. And it makes sense because in the beginning, maybe you start from a random model, you learn a lot by training your model, and then in the end, while you are converging to a good solution, that the information gain is lower. And also, layer by layer, we already know that, for example, the previous layer and the latest layers, they contain different kind of information. And so they are updated at different stages during the training loops, and also with a different kind of scaling factor. So this is important. So we are able to group together coefficients in the net. And you can think of this also as directly related to the rate that we use to communicate those updates. And this is the key kind of property of KLMS, that we want to send only the new acquired information to the server and not kind of send redundant information to congest the network. So how it works in practice? So how can we send these updates with just these few bits per parameter. So the idea is that to apply importance sampling, as I said, I will just briefly go through this. Imagine we want to send just one coefficient W. Both the client and the server, they share the global knowledge, so this distribution P on the first coefficient, for example, of the network, and they also share some random C. So they can both generate the same sequence of samples, candidate sample for the first coefficient, imagine W1 up to WK. This is superscript to indicate candidate for the first coefficient. And then the client will weight those coefficients by applying these, basically these alphas, where each alpha is computed by using the local distribution Q divided by the global distribution P. Of course, this is not known by the server, but only by the client. We normalize those weights, and then we can take a sample from the new distribution pi, that is basically a distribution over the indices of this sequence. And then you obtain this K star, and the client will just send the index of basically the K star value to the server. Of course, we just spend log 2 of K bits because we have K possible samples. And so we can, with the log K bits, we can represent any sample within this sequence. And the server can then decode just by looking at the K star and take the K star sample in the sequence. And that is the candidate value for the coefficient W in the network. This is important sampling applied to this strategy. And there is, of course, a relation between the K's, how many samples you take per coefficient, and the accuracy of the estimation of the new updated server. And there are some theoretical results in the paper that I will avoid to explain here. And with KLMS, as I said before, we have dynamic rate adaptation. So what I showed you before in that 3D plot, we also see here. So if we use uniform binning, you can see here we have a uniform rate, meaning the number of bits per coefficient is fixed at 0.125. But the K divergence, actually the dotted line, is going down as the train basically rounds go on, because of course we are learning less and less information from the local updates. As while applying the adaptive counterpart of KLMS, we are able to, not in the beginning, but then to match the K divergence. And this means that we are sending only the meaningful information from the client and to the server without any network or resource wasting. And the bits allocation is optimized over layers and over the rounds of the whole training strategy. Now, what we did also, then we took this KLMS and we applied on top of many existing strategies, for example, FedPM, QHD. We have also the Bayesian counterpart QLSD, that is QHD in the Bayesian setting, and also other, and we compare against other baselines. And as you can see here, we perform a lot of simulation by creating a new block, the KLMS block in Flower, and some other compression block in Flower. And then this is the accuracy versus bit rate trade-off you can see. And you can see that if you take one of the baseline and you apply KLMS on top of them, the KLMS is able to push those points toward the top left part of the plot, meaning that you may be able to achieve the same accuracy, if not better accuracy, by spending less bits per parameter. And of course, these are IAD scenario, but there are a lot of simulations and results in paper. And this is also for the Bayesian counterpart for QLSD. Here, as I said before, LSD or QLSD or any Bayesian strategy naturally is the KLMS naturally adapt to this Bayesian strategy, because in this way we already have the Q's and the P's. So the model updates in form of probability distribution, as well as the global model in form of probability distribution. So in this way, it should be like the optimal way of representing and coding the updates from the client to the server. As you can see again here, we can outperform QLSD in this simulation scenario. And with this, I just conclude my presentation. And I wanted to highlight that KLMS is a novel compression and coding module that can be applied on top of many existing strategies. It can improve the accuracy versus rate trade-offs, leading to very good accuracy, even in very communication constrained environment. And we have numerical results you can find in the paper. And also in the paper, as I said before, basically you can find theoretical findings where we are just extending the importance centric performance as a function of K in the distributed scenario. And this is interesting for kind of federated learning, kind of new compression algorithms.
Okay, well, Francesco, I think this was a great talk, and I saw some super strong results in the previous 2 slides, so I definitely gonna take a look at the paper. I have 2 questions here from people. One, which I think will be maybe useful for a lot, is like in easy words, like for example, looking back at the KLMS coding scheme slide. One question that I kind of also echo, yes, is so the client, in the end, like in plain words, the client is not communicating weights to the server, right? Is it fair to say it's communicating like a distribution that the server needs to sample? And
so exactly. So the basically the subtle part here is that the client has to communicate a new weight update, right? But you can think of it as okay, the client is uncertain about the real value of the update because there is this quantization kind of stage. And so actually in practice, what is communicating is an index of a sequence. Now, the point is that the way the server can produce the sequence and the way the client weight those indices in the sequence is approaching the distribution queue that is only known by the client. So this is, so basically, if you think of it, when K is very, very large, when you sample according to this kind of file method, in the end, you obtain a sample according to K, even though the server does not know K. So I don't know if that is...
would that sampling that the server does, it might not result, that sampling that the server would do, it doesn't necessarily result in the same result that the client has, but I guess if this distribution is sharp enough, it will, right?
Exactly. So in the end, if this K is finite, basically the sample the server can obtain is slightly different. So it's coming from a slightly different distribution from the one known by the client queue. As K is larger, these two distribution basically converge to the same distribution. But of course, as K is larger, the rate also is larger because this is the number of samples we need to use to code just one coefficient. And as you can see in log 2 bits is the size of the message. So yeah, exactly. So the server will use an approximate distribution to try to insert the one known by the client. And you can kind of tune this accuracy versus rate trade-off by, for example, taking more samples for each coefficient.
Okay. Then a follow-up question I think could be related to this is, how does KLMS cope with clients that suddenly get new data, let's say? Because I think a lot of the strengths of KLMS is as the magnitude of the gradients starts going down, so the models need to change less and less, it can really, how can I say, it really benefits from that. But if now there is suddenly some extra data, there is a huge jump in the gradient magnitude, is it going to... The bits explode, I guess, right?
Yeah, that's a good question. And actually, you don't see it maybe clearly from here, but the point is that if that happens, it means that now the K divergence starts increasing, as you said. And here, maybe in the first round, so actually what we do is in order to adapt the size and the indices of each of the bins in the network to group together coefficient and create the messages, what we did is we start from some random guess, and then as you can compute the KL divergence locally with the global ones, and as this basically, if the rate is not good for each pins, what we do is we adapt the size and the indices of those pins, and we send these new indices from the server to the client once every kind of X iterations, depending on how they diverge. So what happens, what we saw is that in the beginning, maybe we adapt the the position of these pins a few times, and then you don't adapt again because there's no need to, there's not so much difference between the gap of the pins locally and globally. But as you said, if the new data arrive, then maybe this gap is larger, for example, at around 60. For KLMS, that would mean that we will see a jump again, and because maybe the first round you are suboptimal, and then after the first round those data has changed, maybe the server is informed about that, and so it will distribute a new kind of pins optimization. So basically, it will distribute the pin indices so they can group together kind of optimal coefficients, and so then we start decreasing again. So yeah, of course you will see. So basically, KLMS can adapt to this new distribution of the data, and but of course you will notice an increase in the rate and then decreasing again.
Yeah. Okay. Interesting. Sounds this final summary of what you said kind of remind me to other non-related things like video codecs. When there is a change in the content of the video frame, there is a big spike on bitrate. When
exactly. There is
Okay, cool, interesting. Okay, I have one final question from Brian on Zoom. Is the source for KLMS available on GitHub?
Yeah, so we are kind of cleaning the repo, and it will be shortly be available on GitHub also because it is related to the conference paper. So yeah, you will find all the code on GitHub.
Okay, great. Then I think this is everything. Brian says thank you very much, so that's good. So thank you very much, Francesco, once again. I'll just wrap it up with a final slide. So thank you everyone for joining this Flower Monthly, and the next Flower Monthly will be a month from now, roughly, which will be Wednesday, May the 1st, again at 4 p.m. UTC. So hopefully I'll see you all and many more of your colleagues online next time. And as usual, all these talks and, well, in general, the whole Flower Monthly will be uploaded to YouTube in the coming days. So stay tuned for that as well. Well, thank you very much. Thank you, Francesco, and everyone else. Bye.
Thank you. Bye-bye.